Look at this syllabus point. Checksums and check digits. You know the definition. You walk into your Cambridge 0478 exam feeling totally confident, right? And then you walk out having dropped an entire grade boundary. Why? Because you wrote a generic textbook definition instead of an engineered examiner response. So in today's explainer, we're going to decode the mark scheme like a secret language so you never ever lose these easy marks again. Let's get into it.
0 out of 4. Man, that is the painful reality for thousands of IGCSE computer science students every single year. They just lose full marks on what really should be an absolute gift of a question. And look, the stakes here are massive. In the 0478 syllabus, a 4-mark question is a heavy hitter. Dropping these marks just because of poor exam technique, that can literally be the difference between an A and an A star. Okay, let's dive into this. Picture a student who wrote a perfectly confident but completely generic definition. You know, something like, a checksum is a value used to check if data is corrupted. Sounds okay, right? Well, that gets a massive 0 marks from the examiner. Writing generic labels without process steps or context is the absolute fastest way to drop grade boundaries. Because the examiner, they aren't looking for a dictionary. They are looking for applied computer science. Section 1. Why revision fails and why generic answers fail. So, looking at the source material, it highlights a very specific chain of common errors. Things like using vague wording or confusing memory and storage. Or, and this is a big one, disastrously mixing up validation and verification. But above all, the biggest mistake is failing to anchor your answer to the context. You see, computer science mistakes frequently happen when we confuse nearby concepts. Like, you memorize that a check digit checks data, but you completely forget if it checks the format or the actual truth. And let me be super clear about this. Cambridge examiners ruthlessly punish these generic answers. If you're just dumping facts onto the page, you are basically throwing points away. Generic responses rarely gain full marks. Context is literally everything. Whether the exam scenario is a school, an office, a network, a robot, or a banking system, your answer absolutely must stay inside that specific context. You have to map the digital problem to the exact device or data involved in the prompt. You just cannot treat a banking system and an industrial embedded system exactly the same in your written response. It just won't work. Section 2. The 4-prompt memory framework for exam adaptability. Right, here is your ultimate checklist for exam adaptability. Whenever you study a concept like checksums or check digits, you need to be able to answer 4 prompts out loud. Number 1, what is it? Just identify the core concept. 2, how does it work? You need to explain the clear, sequential, mathematical, or logical process, like block addition for a checksum. 3, where is it used? Identify the exact data or hardware mentioned in the prompt. And number 4, why is it better or worse than an alternative? Because knowing a system's limitations is just as important as knowing its functions. Seriously, if you can't hit all 4 of these steps smoothly, you just aren't ready for the exam. Now, in a moment, I am going to show you the exact examiner clue that changes a checksum answer from a measly 1 mark to a perfect 4. But first, you really need to see this 4-prompt framework applied to a real scenario. Because otherwise, that critical clue, it'll just fly right over your head. Section 3. Flawed versus perfect answers. Taking theory to practice. Let's look at a classic exam-style scenario. Straight from the communication and internet chapter, it goes like this. Data is transmitted to an industrial control robot. How is a checksum used to ensure data integrity? Notice the specifics there. It's not just abstract data, it's data transmitted to an industrial control robot. That specific device is your anchor. So your answer must revolve around that exact industrial robot. Now, what's really interesting about this is the stark contrast in technical depth. The flawed student answer just says, it calculates a value to check for errors. I mean, that gets 1 mark, maybe, for vague recognition. But look at the top band answer. The sender calculates the checksum using a specific mathematical algorithm on the block of data and sends this resulting value with the data. The robot recalculates the checksum upon receipt using the exact same algorithm and compares it to the original. Do you see how it explicitly names the device, the robot, and walks through that mathematical sequence? That's what you need to do. This brilliantly illustrates the rubric decoder. Notice the progression here. First, the concept, checksum. Next, the evidence or data, transmitted data. Then the scientific reasoning. It doesn't just check. The system mathematically recalculates the payload block data upon arrival and compares the 2 distinct values to see if bits were altered during transmission. And finally, the examiner wording. Words like sender, robot recalculates, and compares. This top-band answer doesn't just name-drop the technology, it actually proves true applied understanding of the underlying logic.
Section 4. Spot the fatal error. A classic trap. Okay, I want you to act as the examiner for a second. Read this seemingly perfect answer. A school database uses check digits. The check digit verifies the student ID is correct. Find the fatal error. I mean, it looks right? It sounds technical, it names the school database, but it is fundamentally flawed. What is the hidden mistake? Think about it for a second.
Did you spot it? It's that sneaky little word verifies. Check digits validate data entry. They check the format and the logic. A check digit uses a mathematical algorithm, like modulo 11, on the ID number to ensure it simply wasn't mistyped. It takes each digit, multiplies it by a specific weight, sums those up, and divides by 11 to see if the remainder matches the final appended digit. It is pure validation. They absolutely do not verify if the student ID actually belongs to that specific student or if it's the absolute truth. Confusing validation and verification is a classic wrong turn in computer science that will instantly cost you the mark, no question. So the crucial point is captured perfectly in this quote from our source text. Students often know the theory, but lose marks because they do not anchor their explanation to the details provided. Or, like in our last scenario, they use nearby terms interchangeably when they actually mean completely different things algorithmically. You've got to use precise terminology, and you have to connect it directly to the given digital environment. Section 5. The next code layer and an unresolved vulnerability. We've mastered how a checksum proves data integrity during transmission to a robot, and we definitely know how to avoid those generic answers now. But here is a massive unresolved problem in this digital scenario. What happens when the checksum matches perfectly, but the data has still been compromised? Think about it. A checksum only spots accidental errors in transmission, like flipped bits from electrical interference. It does not spot intentional, malicious tampering, where a hacker alters the data and recalculates a new matching checksum to trick the robot. There are serious protocol vulnerabilities that this mathematical method alone simply cannot solve.
To solve that exact vulnerability and to master the next hardest skill in the 0478 syllabus, you really need to understand cryptographic protocols. It is the mandatory next step to secure your top grade and fill that huge security gap. Subscribe to our YouTube channel, Ace the Exams, at @acetheexams_IGCSE to excel in your Cambridge examinations. Join us in the next explainer to decode this final layer of network security. I'll see you there.